Welcome to Week 6, Lecture 2, ANOVA Continued. Students encountering this statistical technique for the first time often tend to be overwhelmed by the formulas and the mathematics and lose sight of the general purposes for the analysis. So I'd like to present an example whose purpose is really to present a visual image for the concepts of between treatment variability and within treatment variability. We will compare two hypothetical outcomes from the same experiment. The experiment will use two separate samples to evaluate mean differences between two treatments. The following data represents two outcomes. We will have experiment A and experiment B. The data from experiment A are displayed in the following frequency distribution graph. In the figure, we have indicated the between treatment difference by showing the distances between these two means. So the mean for the first group is 8, and the mean for the second group is 12. And so we see that there is a big mean difference between these groups. We also can represent the within treatment differences by using the range of scores for each separate sample. So we have a within treatment for this group, and we have a within treatment for the second group. Clearly, the between treatment value is substantially greater than the within treatment value. This observation can be confirmed by comparing the F ratio for experiment A. So if we were to go ahead and calculate the mean squared between and a mean squared within, we get the following values with a value of 56 for the mean squared between and a value of 0.667 for the mean squared within. And we would get a final F value of 83.96, which is sufficient to reject the null hypothesis with an alpha level of 0.05. So we can conclude that there is significant difference between the two treatments. Notice that the statistical conclusion agrees with the simple observation that the data show two distinct sets of scores. And what I mean is you can see that treatment A is over here and treatment B is over here. So you can look at this and say, okay, I can tell that the people in this group generally score around the value of 8, whereas people in this group score around the value of 12. And because it's so easy to see that there is a clear difference between these groups, that means that there's not a lot of error. And that's pretty obvious when you look at the mean squared within, value is pretty small. Okay? Now, let's look at the data from experiment B. Before we go on, I'd like to point out that the mean difference between the first group and the second treatment group is exactly the same as the mean difference that we obtained in experiment A. However, if you look at the variance over here, the values are very different. So here is the frequency distribution for experiment B. And again, we can identify the between treatment differences. And the between treatment differences, in other words, the mean differences, again, are the same. It's just the difference between 8 and 12. We can also examine the within treatment differences, which are indicated by the range of scores for the first treatment and the range of scores for the second treatment. And what you see is that there's a lot of within treatment overlap between these two groups, which was not the case for experimental A. So now, between these treatments, the value, so now the between treatment value is small in comparison with the within treatment values. So if we compare our F ratio, we can confirm this observation. And so our mean squared between is 56 because the variance between the groups hasn't changed. However, because of this large overlap and because of all the variability that exists within the groups, our error term is now quite large. And as a result, we get a very small F ratio. So the F ratio is not large enough to reject the null hypothesis. Remember, if the mean differences is really small, then what happens is we get chance over chance, and we get an F ratio of 1. So the statistical conclusion is consistent with the appearance of the data if you look at the figure. Looking at the figure, we can see that the scores from the two samples appear to be intermixed randomly with no clear distinction between the treatments. And so what I wanted to point out is that the difference between the two experiments that we talked about is really, it lies in terms of the error term. So the examples we mentioned, they're intended to demonstrate the role of variance in hypothesis testing. Large values for error variance can obscure any pattern in the data and reduce the potential of finding significant differences between your treatments. Therefore, you want to eliminate error as much as possible. In analysis of variance, the mean squared value in the denominator of the F ratio is called the error term. This mean squared value is intended to measure the amount of area variability, that is, the variability in the data for which there is no systematic or predictable explanation. These unexplained differences from one score to another are assumed to be the result of chance. The error term is a standard for determining whether or not the differences between the treatments, as measured by the mean squared between treatments, are greater than would be expected by chance. So, the numerator in the F ratio, the mean squared between, simply measures how much difference exists between the treatment means. So, the mean squared between is simply measuring the treatment effect plus whatever chance that might have occurred. A large value for the mean squared within will result in a larger F ratio. The denominator of the F ratio, the mean squared within treatment, measures the variance of the scores inside each treatment and often represents chance. A large amount of variance can make it difficult to see mean differences. And if you think back to experiment B that we just talked about, in experiment B there was a large amount of variance, and it was very difficult when we were looking at it to determine if there were any real mean differences. In general, the greater the variance, the smaller the F ratio. As noted before, the denominator of the F ratio is commonly called the error term. This terminology is based on the fact that the denominator measures the amount of variability that is unexpected and unpredictable, that is, the amount of variability due to error. For the independent measures design, the error term is always determined by the amount of variability within the treatments. All subjects are treated exactly the same. In other words, the researcher does not do anything to cause variability among the scores within the treatment condition. Any difference that exists within the treatment condition can be explained only by chance error. So, a researcher generally hopes to obtain systematic and predictable differences. A researcher generally hopes to obtain systematic and predictable differences between treatments. The error term is used by the researcher as a benchmark or standard for evaluating the differences between the treatments. If the between treatment differences are substantially greater than the error term, in other words, the mean squared is much larger, the error term is smaller, then we would expect then the researcher can confidently conclude that the differences between the treatments are due to more than chance. In other words, we get a large F ratio. Assumption for the one-factor analysis of variance. The independent measures ANOVA requires the same three assumptions that were necessary for the dependent measure t-test. The observation within each sample must be independent. The population from which the samples are selected must be normal, And lastly, the population from which the samples are selected must have equal variance, also known as homogeneity of variance. And this final assumption is really one of the most important assumptions that we can have for the ANOVA. Before we go on, we really need a notation system to help keep track of all the individual scores and totals for the analysis of variance. So, for the sum of x, or the total for each of the treatment conditions in the ANOVA, it is generally identified as the capital letter T. So we have T for the total, and then in general, it's usually subscripted by something that indicates the groups. In this example, we have group 1, 2, and 3, so we have T sub 1, T sub 2, T sub 3. And so to get the totals, we simply add all the values in the column. So 1 plus 3 plus 1 equals 5. In this example, 4 plus 3 plus 6 plus 4 equals 20. And lastly, 1 plus 2 plus 2 equals 5 again. We need to compute the sums of squares for each group. By this point, I'm pretty confident that most of you can do this, but please feel free to stop the slide and try to compute these values on your own, or possibly put the data in Excel and see if you can come up with the sums of squares that way. So sums of squares, the notation is the same as before. It's represented by SS, and then we have a subscript to represent each of the samples. And so the following values are the values for the sums of squares. Next, we need to indicate a value for the number of scores within each treatment, and that is generally identified by the lowercase n. And so n is how many scores are within each treatment. And if you'll see, there's the same number of people in each of the treatment conditions, and that value is 5. Now we need to compute the mean for each group. Now, the mean is represented by the value of n, and it has a subscript, and you just need to go ahead and calculate the mean as we've always done before, so please feel free to stop the slide and calculate that value. And so here are the values for the means. Now we need to compute the sum of all the x values squared, and that is all the x values in all of the treatment conditions. And so here is simply the sum of every x squared. The next value we need is the sum of all the scores within the research study. So this is just the sum of x, and is often noted or identified by the letter G. So for G, go ahead and add up all the scores. You should get a value of 30. The total number of scores in the entire study can be specified by the capital letter N. We have 5 people in each group, and we have 3 groups, so we have a total of 15 individuals. Lastly, we use the letter K to identify the number of treatment conditions, or the number of levels, or also known as the number of groups. So in this example, we have 3 groups, so K is equal to 3. Now we have all the values that we need to go ahead and compute our final F ratio. But before we can do that, we need to talk about ANOVA and the formulas that we need for the ANOVA. The entire process of analysis of variance will require 9 calculations. This table that you see here is called a source table. It's a very common way to present the values that you get in ANOVA. In the source table, we have, and also for the calculations of our final F ratio, we have 3 values for the sums of squares, and they will be in the following little slots. We also have 3 values for the degrees of freedom, 2 variances, our mean squared between and our mean squared within, and then we're going to use those 2 values to compute the F ratio, which will be presented here. Now, However, these 9 calculations are logically related and they are all working together to find that final F ratio. So, analysis of the sums of squares. ANOVA requires that we first compute the total sums of squares and then partition this value into 2 components, the between treatments and within treatments, which will be represented here. Then after that, we need to calculate. So let's start off with the total sums of squares. As the name implies, the sums of squares total is the sums of squares for the entire set of n scores. We calculate this value by using the computational formula for the sums of squares. So the sums of squares total is generally indicated by SS subtotal. And the formula, if you think back to what we've done before, is the sum of every x value squared added up. And here for G simply represents the sum of all the x values, then squared, divided by n. So this is exactly what we did when we did the sums of squares for one group. But now we're not doing it by group, but we do it for the total or the whole experiment. So now let's go ahead and apply this formula with the data set that we have. If you can flip back to the data values that we have, we are going to use the following values to find our sums of squares total. So we take these values and plug it into the formula. And for the sums of squares total, you simply go ahead and do math, and you should get a value of 46. So now let's go ahead and take this value and place it within our source table so we can keep track of these values. And you'll see that if you place them in the source table, it'll make it easier for you to get your final value. So the sums of squares total is 46. Now we need to get the sums of squares within treatment. And so to find the overall within treatment sums of squares, we simply add the values together. So in other words, for the sums of squares within, we simply sum the sums of squares inside each treatment. And if we go back to our data, we have the sums of squares for each treatment already calculated. So now what we simply need to do is add those values up, and we get a value of 16. So let's go back to the source table and go ahead and put our value in here. Now, if you think back to what I've told you before, the sums of squares total is made up of the sums of squares between and the sums of squares within. So we could, at this point, simply calculate our between treatment value by simply taking 46 and subtracting 16, which gives us a value of 30. But we're going to go ahead and use the formula and use this just to double check and make sure that we're doing the right calculation. So the between treatment sums of squares, in the between treatment sums of squares, we are measuring the differences among the 3 treatment means. And so we will use the following formula for the sums of squares between treatments instead of using the total sums of squares. So for the sums of squares between treatments, the formula is the total in each group squared divided by n subtracted by the total score for the entire experiment squared divided by the individuals. And so we have all the values here. I've highlighted in red so you can see. So we just take these values and go ahead and plug them in, and then we just simply solve. And what we get for our sums of squares between treatments is 30. And if we go back to our source table and we plug it in and we look at this value, it's exactly what I expected it to be. Because again, the sums of squares total is simply the sums of squares between treatment plus the sums of squares within treatment. So 30 plus 16 is 46. Analysis of the degrees of freedom. The analysis of degrees of freedom follows the same patterns as the analysis of sums of squares. We start out with the total degrees of freedom. And the formula for the degrees of freedom total first starts off with the notation, which is just degrees of freedom, df, with the subscript total equals the total number of individuals in the experiment subtracted by 1. So if we go back to our data, that is the value of 15, and we simply subtract 1 from that. We get 14 for our degrees of freedom total. Let's go ahead and grab our source table and plug in the value 14. And now let's compute our within treatment degrees of freedom. So for the within treatment degree of freedom, we simply have degrees of freedom sub within is equal to the total number of individuals in the experiment minus the levels or the groups in the experiment. So in this example, we have those values highlighted here in red. So let's go ahead and plug those values in. And when we solve for that, for our degrees of freedom within treatments, we have a value of 12. Let's go ahead and plug that value into the source table. And now you should be able to eyeball this really quick and guess what our degrees of freedom between subjects is. You should guess that that would be a value of 2, but let's go ahead and use the formula. The between treatments degrees of freedom is noted by degrees of freedom df subscript between treatments. And it is simply the total number of groups subtracted by 1. And so if we go back to the data, we have 3 groups. And we take the value of 3 and we subtract 1 and we get a value of 2. So let's go ahead and go to the first table and put that value in. And as I mentioned previously, the degrees of freedom total is simply degrees of freedom between plus degrees of freedom within. Thus, the value of 2 plus 12 should equal 14, which it does. Now that we've completed all these formulas, on to the next step, and that is calculating the variance or the mean squared and the final F ratio. So the F ratio is simply the mean squared between treatments over the mean squared with treatments. Well, the value for the mean squared is just another name for variance, is simply the sums of squares over the degrees of freedom, which should be pretty familiar for us because we have calculated the variance many times in this course. So for the mean squared between, we simply take the variance between the treatment groups, or the sums of squares between treatments divided by the degrees of freedom between treatments. So if we take our source table, we simply take the value of 30 and divide it by 2. So let's go ahead and place that there, and we solve for it, and our answer is 15. And now we can plug 15 into the source table. Now we need to find the mean squared within treatment. And the mean squared within treatment is just another word for the variance within treatments. And the formula for that is simply the sums of squares within treatments over the degrees of freedom within treatments. And so here we have values for our sums of squares within and our degrees of freedom within. And so we simply take 16 and divide it by 12, which gives us a mean square within treatment of 1.33. Now, we simply need to work backwards and take these two values and plug it into the F ratio. So the F ratio, again, is the mean squared between treatments over the mean squared with treatments. And here's our source table that we've been keeping track of all the values in as we've gone along. And we simply need to use the values for the mean squared. So we go ahead and place the value of 15 and 1.33 into the formula, and we solve for F. And we get a value of 11.28 for our F ratio. And we go ahead and place that value into the source table. And there you have the ANOVA summary table. The ANOVA summary table is beneficial for 2 reasons. One, it provides a concise way for presenting the results from your analyses. Also, it's a great way to keep track of the values that you have and to double check your work as you go along to ensure that you're doing everything correctly. Okay. Now let's talk a little bit about the distribution of F ratios. When the null hypothesis is true, the numerator and the denominator of the ratio are measuring the exact same variance. In other words, when the null is true, there are no group differences, then the values for the numerator and the denominator are both measuring chance and thus should be equal. And if that is the case, we would expect the value of F to be around 1. The question comes up is what values are considered close to 1 and what values are considered far away from 1? To answer this question, we need to look at the possible F values. That is, we need to look at the distribution of F ratios. So there is a table in our book like we had for the t-test and like we had for the z-test that we can look up the values for the F ratios. There are two obvious characteristics of ANOVA. Because the F ratios are computed from two variances, the F values will always be positive numbers. When the null is true, the numerator and the denominator of the F ratio are measuring the same variance. The two sample variances should be about the same size, so the ratio should be near 1. In other words, the distribution of F ratios should pile up around 1. Thus, we need to use the F distribution table for analysis of variance. Unfortunately, because our book doesn't go into detail on analysis of variance, it also doesn't provide us a table for analysis of variance. So if you do need the table, if you're computing any values by hand, you can feel free to just do a quick Google search for the F distribution table and you should find it no problem. However, in this class, we'll probably just use Excel to get the value for the F distribution table, so I'm not going to push too much about that. But to use the table, what you will need is you will need to know your degrees of freedom between, your degrees of freedom within, and whatever alpha is. And it's pretty straightforward. We'll talk a little bit more about that in our very last lecture. So our next and our last lecture for this week, we'll go over an example of analysis of variance. And so hopefully so far you guys have a good idea of when we use analysis of variance and the theoretical or the conceptual view of what analysis of variance is. And so then we'll go through an example and hopefully alleviate some of the math woes that you guys have. We'll also talk about it in terms of Excel. Thank you for your time.